Good day, students. On this clip, we're going to be going over the introduction to analytic geometry. So let's write down the title of the notes. Introduction to analytic geometry. Analytic geometry. Okay? We're going to start with the first set of tools. Actually, the first tool we need in order to start analyzing geometric objects represented by coordinates. And the first and most important tool we're going to learn is the whole idea of computing distance. Okay, so we're going to start by writing down what the distance formula is. The distance formula. All right. So what is the distance formula? Let's write down what it is. The distance d in units, that's what we're going to be focusing on today, in units between 2 points, specific with coordinates x1, y1, and x2, y2 is given by note this subscript right here is 1, so x1, y1 is given by d equals the square root of x2 minus x1 square plus y2 minus y1 square. Okay, so there you have the distance formula. Now, where on earth did this formula come from? It looks like a complicated formula, but it turns out that it is a version of a simple formula that you've studied before. So let's derive this formula, derivation. In this part, you're going to see where this formula came from, and hopefully this explanation will help you to remember how to derive this formula in the future. Okay? So to derive this, all we need to do is we just need to draw a coordinate system, and we're going to just pick 2 arbitrary points and label them x1, y1. Okay? So let's say we have the first point somewhere here. We're going to call it x1, y1. Let me make it a little bit bigger. So this point right here is x1, y1. And then let's pick another point somewhere here. And this point is going to be x2, y2. Alright, so how do we compute the distance between these 2 points? So let's call this distance between these 2 points, let's call it d. Alright, so can we develop a formula to compute what this length is? Well, let's see, let's label the values of these coordinates. Alright, so this one on the x-axis, this is x1. Let's scroll down a little bit for you all to see. x1 and this is y1. That is why the corresponding coordinate is x1, y1. And then over here is y2. This is your y-axis. This is y2. And over here is x2. Alright? So that's why I have these coordinates. Now, in order to compute this length, I'm going to create something. I'm going to make this into a right triangle. So make it into a right triangle like this. So if I can compute this length and this length, then I will be able to use a formula that you've seen before in geometry to compute what the actual length of this side is, right? So what are the coordinates of this point before we start finding the value of the lengths? This point is x2, y1. So this point right here is x2, y1. Alright? Now I need to find the length of this piece right here. What is the length from here to here? How far is it? So from here, to compute that length, that's going to be x2 minus x1. That's the length from here to here. Alright? Let me do that again with a different color so you can see it clearly. So this length right here, the length on the bottom is x2 minus x1. And then this length from here to here, going up and down, is vertical, so it's y2 minus y1. Okay? So what formula can I use to compute this length right here? I can use the Pythagorean theorem, right? So if I call this, I can call this side A and call this side B. It doesn't really matter which you call which. And then this side right here is going to be C. All right. So the legs of the right triangle are the A and B, and the hypotenuse is the C. So what does the Pythagorean theorem tell me? It tells me that C squared is equal to what? A squared plus B squared. All right. But since A is since B is this distance right here, and this is that distance right there, we can plug in their corresponding values, right? So C squared, I can rewrite C squared as D. So we're going to have D squared equals, let me write B squared first because it doesn't make any difference. So I can write x2 minus x1 squared plus y2 minus y1 squared. Okay? So this is simply a squared and this is simply b squared. So to get d by itself, to finish this up to get our formula, we're just simply going to square root both sides, right? So the square root of this whole expression we have on the right side, which is x2 minus x1 squared plus y2 minus y1 squared. So this is where the formula came from. This formula is just a version of the Pythagorean theorem. Okay? Alright. Now, we're going to use this formula that we derived to try out some examples. Alright? So, let's try out some examples. Example 1. Example 1. Find the distance between 9 comma negative 2 and 12 comma negative 14. Okay? Now to find the distance, we're going to be using the distance formula here. So the distance formula, again, d is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? So in order to avoid making mistakes when I'm substituting, I'm going to label my points x1, y1, and then x2, y2. Alright, so I'm going to substitute the corresponding coordinates into this equation, and then go ahead and compute my distance. Okay, so my distance is the square root of x2 minus x1, 12 minus 9 square plus y2 minus y1, which is negative 14, minus negative 2 square. Okay? Alright, now we're going to use the properties of arithmetic to simplify this. So we're now going to have the square root of 12 minus 9 is simply 3. 3 square plus this, I'll put a parenthesis here. This minus and this minus makes this a plus. So minus 14 plus 2 is going to be negative 11. Negative 11 squared. Alright, and then that further becomes the square root of 9 plus 121. I'm sorry, this is supposed to be 12. And it's supposed to be 12 right here. So 12 squared is 144. Alright, so let me fix that real quick. So this is negative 144, negative 12 squared. And then when you square that, this piece right here becomes 144. Okay? Now there's a common mistake most people make. When you have a sum of two square roots, please do not make this mistake. Some people say this is the square root of 9 plus the square root of 144, and they make that 3 plus 12, which is 15. This is absolutely wrong. Note, square root does not distribute into plus or minus. It only distributes into multiplication and addition. Okay? So keep that in mind. Don't do this. You must simplify this sum and difference completely first before you take the square root. Alright? If you cannot simplify, you just leave that as your answer. Alright? So this one has to become, the correct answer for this is the square root of 153. Okay? Now, can I simplify this? Let's verify. 153. If I add the 3 digits, it's divisible by 3. 1 plus 5 is 6 plus 9. So that means I can take 3 out of here. And I'll be left with 51. Take out another 3. And I'll be left with 17. 17 is prime. So when I'm taking the square root of 153, these two 3's repeat, so they break out as 1. So basically, square root of 153 is 3 root 17. Alright? So our final answer is 3 root 17. So what does this answer mean? It just basically means that the distance between the two given points, is 3 root 17 units. Okay, so for the classwork, I'd like you to write this conclusion. It shows me that you understand what the answer means, all right? All right, welcome back, students. In this part, we're going to be going over how to apply the formula we just learned, which is the distance formula. So right on the title, this is basically application to geometry. Okay, so we're going to be applying the concept we just learned, which is the whole idea of computing distance. We're going to apply it to geometry. All right, so we're going to be doing this within the context of a parallelogram. So let's start out by defining what a parallelogram is. So definition. Okay, a quadrilateral is a parallelogram if one pair of opposite sides sides are congruent and parallel. The sides are congruent and parallel. Okay, so that's sufficient to show that a quadrilateral is a parallelogram. All right, so the key word here is parallelogram. Okay, so with this definition, let's take a look at a diagram and see if we can have a symbolic perspective to the definition we just wrote. So let's just draw a regular parallelogram like this, and let's label the vertices, okay? So A, B, C, D. Alright, so what does our definition mean? It means that if I pick any two sides, and I can any two opposite sides, if I can show that they're parallel and congruent, then that's sufficient. So in symbolic form, we can say parallelogram. Let me rewrite my parallelogram symbol. So I can write it like this. Parallelogram A, B, C, D. I'm sorry. So you can rewrite it as A, B, C, D. A, B, C, D is a parallelogram. That's a symbol for parallelogram. If this is a small parallelogram I'm trying to draw here. I keep messing it up. So parallelogram ABCD is a parallelogram if segment AB is congruent and parallel. This is a shorthand for parallel to segment DC. All right, or segment BD is congruent and parallel to segment AC. Alright, so what does that look here? So AB is congruent to DC. We can just put one tick mark there. Parallel means that we can just put one arrow. Alright, so that shows that it's a parallelogram. Or alternatively, we can compare AC and BD. We'll put two tick marks here. and then 2 arrows here. Okay, so that shows that the opposite sides are congruent and parallel, and that is what it means to be a parallelogram. All right, so let's consider this within the context of an example. Example 2. Um, prove that the quadrilateral having the vertices 2, 2, 8, 8, 13, 4, and 7, negative 2 define a parallelogram. Okay, so that's the task that we want to show here. Alright, so to do this, we're going to start out by attempting to graph these points. We're going to graph these points to the best of our ability, and then we're going to label them and basically prove using this definition that this is a parallelogram. Okay, so let's graph these points. I can look at my points here. I can see that my biggest x is 13 and my smallest x is 2. So we're going to stretch out our x-axis as far to the right as possible. My biggest y is 8 and my smallest y is negative 2. So we just need to go down 2 points. Well, let's make it 3. Go down 3 and go up way past 8. Alright? So let's draw a coordinate system like this. Now let's graph the points. I'm going to graph the points in the following order. The first one is 2, 2. So we have 2, 2 right here. Alright, and then my next point is, so this is 2, and then the next one is 8, 8. So 1, 2, 3, 4, 5, 6, 7, wait, 2, 3, 4, 5, 6, 7, 8. So that's 8. This is 2, 2, and then we're going to go up 2, 3, 4, 5, 6, 7, 8. And that's 8. There you have a point. Alright, next one is 13, 4, 8, 9, 10, 11, 12, 13. And then go up 1, 2, 3, 4. And then the last but not the least is 7 and negative 2. So 7 right here, negative 2, 1, 2. Alright, so there goes your points. I'm going to connect the dots. And the question is do these points define a parallelogram? Alright, so we can't just assume based on the sketch that it is a parallelogram. We have to show rigorously that it actually is a parallelogram. So I'm going to call this point A. Point A is my 2, 2. I'm going to call this point B. Point B is my coordinate 8, 8. I'm going to call this point C. Point C is my coordinate 7, negative 2. And then point D is my 13, 4. So why am I labeling these points? Well, you're going to see in a minute. It helps me to keep them organized. So to do my proof, let's do the proof. So for the proof, what do we want to show here? Okay, so for the proof, if we can show that one pair of opposite sides are parallel and congruent, that's sufficient. Okay, so let's pick AB and DC. So we must show that segments AB and DC are what? That they are congruent and parallel. Okay, if I can show that they're congruent and parallel, then that means that this whole quadrilateral is in fact a parallelogram. Alright, so first part is we want to do the test for parallelity. Okay, the test for parallelity. Okay, so basically what we're trying to show here is segment AB parallel to DC. Alright, so here question is I want to show that AB is parallel to DC. That's the goal here. Okay? Alright, so first of all, we need to find the slope of the two segments. So what's the slope of segment AB? Slope of AB. So what's the slope formula? It's rise over run. So it's basically y2 minus y1 over x2 minus x1. Okay? So we're using points A and B here. So this is my 1, this is my x1, y1, and this is my x2, y2. So my y's, I'll subtract my y's, 8 minus 2, because this is my x, y2, x2, y2, y1, over, then I'll subtract the x's. This is my x2, x1, 8 minus 2. 8 minus 2 is 6 on the top, 8 minus 2 is 6 on the bottom, so the slope of segment AB is 1. Okay? Now next we need to find the slope of segment DC. Using the same formula, y2 minus y1 over x2 minus x1. Okay? So this is my x1, y1, this is my x2, y2. So to find the slope, I'll subtract the y's, which is 4 minus negative 2. And then over the difference of the x is 13 minus 7. Alright, since this is two minuses, I'll multiply them and it becomes a plus. So I have 4 plus 6. 4 plus 2. 4 plus 2 over 6. So that yields 6 over 6. Plus 6 over 6, final answer is 1. Alright? So since their slopes are the same, what can we say here? So the slopes are the same, we can conclude that segment AB is parallel to DC. Okay? Since they have the same slope. Alright, now we're done showing that the test for parallelity holds. Now the next test we want to show is test for congruency. Okay? Test for congruency. So we've already selected our two test segments, AB and DC. So to test for congruency, all we just need to show here is we just need to show that segment AB is what? Is congruent to segment DC. If we can show this, then we're done. Okay? So how do we show that these two segments are congruent? We just use a distance formula to compute the distance of the 2 points, between the 2 points. Okay? So to write this in notation, let's write down the distance formula first. Distance formula D is equal to the square root of x2 minus x1 minus x, let me write it properly, x2 minus x1 squared plus y2 minus y1 squared. Okay? Alright, so that's what we're going to be using. So length of AB can be written as the absolute value of AB, like that. That means the length of segment AB is going to be the square root of the distance, the difference between the x's and the y's. Okay? So if you look at your graph, we want to subtract the x's. The x's are 2's, and then we're going to subtract the y's. So for this one, x2 minus x1 is going to be 8 minus 2 square for the x's, and then for the y's is going to be the same thing, 8 minus 2 square. Alright, so x2 minus x1, y2 minus y1. If you look at AB, this is x1, y1, x2, y2. So you subtract the x's and you subtract the y's. Alright, so that's how you do it. Alright, so what does this give us? This gives us the square root of 8 minus 2 is 6 squared plus 6 squared. Alright, it becomes the square root of 36 plus 36, which equals the square root of 72. Alright, we can break this down. 72, take out 2, 2 goes in 72 36 times, take out another 2, 18, take out a 2, 9, and then 3. Alright, so these two 2's come out as a 2, and then these two 3's comes out as a 3. Alright, so this final answer, the simplified form is going to be 6 root 2. Okay, so 6 root 2 is basically what 72 is, 6 root 2. And that's the length of segment AB. Alright, now we also need segment DC. The length of segment DC, if I can show that that is the same as the first one, I'll have accomplished my goal. Alright, so we're going to use the same distance formula, x2 minus x1 squared plus y2 minus y1 squared, the square root of that, sum, to give me the distance. Okay, so if you look at our shape, this is my x2 x1 y2 y2 y1. Okay, so I'm going to be subtracting them. So x2 minus x1, I'm going to have 13 minus 7 square plus y2 minus y1 is 4 minus negative 2 square. Okay, so that becomes the square root of 13 minus 7 is 6 square. 4 minus minus 2 is the same thing as 4 plus 2, right? So it's going to be plus 6, because you can slash and dash that. This 2 becomes a plus right here. So 4 plus 2 is 6. So that becomes square root of 36 plus 36. That is exactly what we have up here, right? With 72, which is equal to 6 root 2. So since the distances are the same, we can conclude that segment AB is congruent to segment DC. Alright? So we now have to write our concluding remark. Our concluding remark is as follows. Since AB, segment AB and segment DC are congruent and parallel, the coordinates that these letters represent, which is the original problem, defines what? Defines a parallelogram. Alright? So this is a good closing remark to basically sum up your argument, and then you put your box of accomplishment. Alright? So that's that. Thanks for paying attention to this presentation. Now we're going to go over some examples using this. Don't forget to subscribe to my videos for future updates, and you can always request for more videos if you want, and I'll try and make them for you. You can find a collection of my clips at math.serve.com, and thanks again for viewing this presentation.